A statistical hypothesis is defined as a formal claim or statement about a specific property of an entire population. To evaluate that claim, we use a hypothesis test, or test of significance. This is the standardized mathematical procedure for determining if a limited sample of data actually backs up the broader statement. Consider the claim that the majority of Internet users utilize two-factor authentication. Mathematically, that means the population proportion is greater than 0.5. To test this, imagine we survey a sample group of exactly 926 users. If our sample returns 464 users, just barely over 50%, our intuition immediately tells us the evidence isn't strong enough. If it returns 925 users, or 99.9%, the proof is overwhelmingly clear. But what if the survey finds exactly 482 users, or 52%? Intuition fails in this gray area. It looks like a majority, but is it high enough to prove the claim about the entire population? This is why we require a formal framework. Hypothesis testing transforms colloquial guesses about ambiguous data into mathematically verifiable decisions. We process our 52% sample through a strict 8-step framework. Step 1 requires us to express the original colloquial claim symbolically. For a majority using two-factor authentication, we write P is greater than 0.5. Step 2 identifies the mathematical condition that must exist if the original claim is false. If a majority is false, then P must be less than or equal to 0.5. Step 3 splits these two expressions into our formal hypotheses. The alternative hypothesis, denoted as H1, is strictly defined as the expression that does not contain equality, so H1 is P greater than 0.5. The null hypothesis, denoted as H0, is the expression where the parameter simply equals the fixed value being considered. Here, H0 is P equals 0.5. Establishing the null hypothesis provides a fixed mathematical baseline. It is the exact starting point against which we will test our collected evidence. Step 4 sets the significance level, represented by the Greek letter alpha. This is the probability value used as the strict cutoff for determining when sample evidence is strong enough to matter. Specifically, alpha represents the allowable risk of mistakenly rejecting the null hypothesis when it is actually true. A common benchmark for this risk is 0.05. Step 5 identifies the relevant test statistic, which depends entirely on the parameter we are testing. Because our claim is about a population proportion and our sample size meets the requirements, we use the normal distribution to calculate a z-score. In Step 6, we compute the value. If we manually plug our 52% sample proportion and our null hypothesis value of 0.5 into the formula, it yields a test statistic of z equals 1.22. However, modern statistical software calculates this using exact fractions rather than rounded percentages. The outputs consistently return a more accurate test statistic of z equals 1.25. These same programs simultaneously output a precise p-value. Here it is 0.106. This probability will dictate our final decision. Manual calculations provide insight into the mechanics, but these precise technological outputs are the modern standard for executing the test. Step 7 forces a decision. We evaluate our test statistic using method 1, the p-value method. Because our alternative hypothesis checks for a proportion greater than 0.5, we follow the logic for a right-tail test. The p-value is the probability of getting a result at least this extreme, assuming the null hypothesis is true. The governing rule here is, if the p is low, the null must go. We compare our p-value of 0.106 to our significance level of 0.05. Since 0.106 is greater than our 0.05 threshold, the p is not low. Therefore, we fail to reject the null hypothesis. We verify this using method 2, the critical value method, which relies on boundaries rather than probabilities. An alpha of 0.05 establishes a critical boundary on our normal curve at a z-score of 1.645. Our sample scored a 1.25, falling short of this green critical region. Once again, we fail to reject. A third method involves confidence intervals. While these align perfectly with hypothesis tests for means and standard deviations, they can occasionally yield different conclusions when testing proportions, requiring careful application. Regardless of the pathway, comparing probability variance or plotting against a strict boundary line, the mathematical threshold for proof remains unbroken by our sample. Step 8 requires us to translate the mathematical conclusion into a non-technical statement. Tracing our specific path through the logic, our original claim did not contain equality, and we failed to reject the null hypothesis. This dictates our final translation. There is not sufficient evidence to support the claim that most internet users utilize two-factor authentication. The semantics here are deliberate. We strictly state that we fail to reject the null hypothesis. The term accept is dangerously misleading. It incorrectly implies the null hypothesis has been proven, when we have only determined the evidence is too weak to abandon it. We also actively avoid multiple negative terms in our final conclusions, stating not sufficient evidence to warrant rejection of the claim of no difference may be mathematically sound, but it is unreadable. Translations must use plain language. The most rigorous statistical test is ultimately useless if its verdict cannot be accurately and clearly communicated to the public. Because we rely on samples, our decisions are probabilities, not certainties. This means our tests can fail in two distinct ways. A type 1 error, mapped to our alpha value, is the mistake of rejecting the null hypothesis when it is actually true. This is effectively a false positive, like approving a medical procedure that has no actual benefit. A type 2 error, represented by the Greek letter beta, is the mistake of failing to reject the null hypothesis when it is actually false. This is a false negative, like dismissing a cure that actually works. This dynamic introduces statistical power. Calculated as 1 minus beta, power is the probability of making the correct decision to reject a false null hypothesis. Let's apply this to a gender selection method trial. If we test the method against a true population success proportion of 0.6, the test yields a weak 18% power. However, if the true population proportion increases to 0.7, the test's power jumps to over 43%. Tower dictates a fundamental rule of statistics. Increasing the difference between the assumed baseline and the actual reality increases our mathematical ability to detect it. Researchers do not just calculate power after the fact. They use it proactively to design experiments from scratch. Consider a clinical trial detailed in the Journal of the American Medical Association. Before collecting any data, the researchers set initial constraints: an alpha of 0.05, a target power of 80%, and a goal to detect a specific drop in coronary heart disease rates from 0.5 down to 0.4. By locking in those exact error and power constraints, statistical software calculates the physical parameters of the experiment. The math dictates they must recruit a minimum sample size of exactly 153 subjects for the trial to be valid. Hypothesis testing ultimately provides the core mathematical architecture for designing rigorous, reliable scientific inquiry from the ground up.